Okay. So the idea of today is we'll show you a web application that was developed to somehow make SISSO a bit more accessible, and also in combination with active learning in FHI aims. And in general, this is also open for discussions and questions from your side. So this could be regarding the talks yesterday. So I hope most of you have also joined webinar talks yesterday from Tom Purcell as well as Lucas Fopper on SISSO and SISSO++, as well as different applications of SISSO and active learning. And if you have questions also concerning those talks, you can of course ask them here, and we'll try to answer them as much as possible. In the principle, we can also connect you directly with the speakers if that's something you need via email exchange. And today I'm here joined also by my colleagues, James and Andre. So they will help throughout the tutorial in case you have questions, or whether it's in the Q&A section or whether you raise your hand and so on to ask questions. So please go ahead. You don't have to wait for, let's say, the end of this presentation and so on. Please feel free to ask questions whenever you encounter them. So you've been sent some small instructions already via email if you've signed up beforehand. If you have not signed up, that is also completely fine. We can work through all this without you needing the initial email. And we'll send links throughout the presentation here inside the chat functionality in Zoom, where you can navigate to the website, download materials, and so on. Okay. But before we actually dive into the actual tutorial, I wanted to give some brief introduction of what the ideas of the web application and the content of this tutorial. So what we'll focus on is active learning and how active learning can accelerate materials exploration. So some of you might already be familiar with the concept. So what we do is we start from some data set. Based on this data set, we can train different AI models. So this can be based on different architecture. In our case, this is SISSO modeling. Via these AI models, where you can train different models based on different data sets, you can get uncertainty estimations, and this allows you to rank candidate materials, which you then can calculate with DFT or whichever other method you want to use for your target property, augment your material space, and again train a new model to gain a new candidate material. So, and this allows you to iteratively identify candidate materials with the desired properties you're interested in. Now, why active learning is interesting in this case is that you actually can quickly acquire exceptional candidates. So this really means candidates with exceptional properties at much lower computational cost than if you would do just random selection. And this ensures reliable predictions through these uncertainty measures that I already briefly explained before, or briefly mentioned before. So the idea here is in active learning, it's significantly cheaper to train the AI models, in our case, than actually running all the density function theory calculations with FHAs. So the faster we can acquire candidates, the more time we actually save in the long run. So that's here really the idea of accelerating materials exploration. And what we have developed is what we think is a user-friendly web application for this specific workflow. So it integrates several points. So that is database management, to always remember your candidate space with the training space and update this throughout the active learning loop. The AI modeling is done, as I mentioned, by SISSO and includes this active learning loop as well. And all the DFT calculations can be done by FHI aims. So this allows you to do accurate and efficient DFT calculations for whatever target property you're interested in. The FHI aims calculations are handled, and the resources for those calculations are handled with Automate2 and actually also Jobflow in the background. So that means these can be offloaded to supercomputing infrastructure, as well as, for example, cloud service if you're really doing more expensive FHI aims calculations and you don't want to do everything on your local machine. Now we note that throughout this tutorial, we have pre-calculated all of the data, both in the training and candidate set with FHI aims beforehand. So the only reason we do this here is to really save a lot of time. So while we click through all the active learning loop and so on, we are not waiting on the FHI aims calculations. But in principle, it's completely also possible to directly run FHI aims via the browser interface. And we'll see in a second also where this actually comes in. And we'll showcase one specific example here. And this is mainly research that was done by Lukas Fopper and his coworkers from some time ago. And this is about identifying perovskites, in our case, cubic perovskites, with high bulk moduli. So on the left here, you see the cubic perovskite cell. So this is an AbO3 crystal structure where A and B can be different elements from the periodic table. And you can see here on the right the distribution across the periodic table of in total 504 cubic perovskites, where we have calculated the elastic modulus, the bulk modulus for all of them with FHI aims at the DFT PB store level. So this here is the GGA level for the bulk modulus. And what we want to find are perovskites in this data set with extremely high bulk modulus. Okay, so to showcase then how this active learning approach works, this is the distribution of training versus candidate space that we have here. So we're starting from a training set where the highest bulk modulus is actually something around the range of 1.3. But we see that in the candidate space, there are more than, or there are a lot of materials with much higher bulk modulus ranging up to around 1.5 EV per cubed angstrom. This is essentially our starting point, and we want to, as quickly as possible, sample the region of higher bulk moduli if possible. Okay, but if you're really interested in how to actually gain a very good SISSO model for these kinds of examples in the perovskites, I really refer to the two publications down here below. There, the focus was really on finding the best performing model for these kinds of test sets. But keep in mind, in our case, we're not interested, or for the purposes of the web app, we are not interested in finding the optimal performing machine learning model, but rather we want to find a good one that is still cheap to run and allows us to quickly sample the landscape. And the good thing here in this active learning approach is while you identify your candidates with the SISSO modeling, so the AI model itself, you don't rely on the predicted property from the model, but rather recalculate it. So SISSO gives us a candidate material, and we then calculate the candidate material with FHI aims to get the actual bulk modulus from DFT. So keep this in mind, we are not as reliant on the actual value that we get out in the end in the modeling. So as long as the model is good enough, we will hopefully get good candidate materials. Okay, so this is basically the introduction for now on the showcase that we'll show you in a second within the app, as well as here the, let's say, the whole point of the active learning loop. Are there any questions before I go for the web app demonstration? Yeah, Andre is also nice enough. He just posted a link. So this presentation is also available as a PDF. You can just download it there via the shared link. And this is just this full presentation in PDF. And as you'll see in a second, we also have some instructions for the app throughout this presentation. So you can also use it as a guide while you do this stuff on your own in the background. So please feel free to download the slides, have a look at yourself. And yeah, but are there any questions up to this point? For questions, again, you can raise your hand if you would like to speak or simply post in the Q&A section. This is up to you. Okay, but at the moment, I don't see any. So I switch my setup briefly. So now you should be able to see my browser window on the left, as well as this, the PDF or the presentation we've just discussed on the right-hand side. Okay, and this is the, let's say the setup I will try to use throughout now this quick presentation to see how this web application works in detail. Yes, exactly. James has just posted the link also for the app. So just navigate to the link there in the chat in your browser window. It should open. There is no need for any user accounts or so you can simply access the app and take a look and then try some stuff out yourself. As again, keep in mind, as noted here on the slides and the webpage, this is currently in beta version. So there might be still small stuff we have to update, but this should be all available for you. As a heads up already, will keep this instance of the app open until the end or the official end of the tutorial. So that is 5:30, 1 hour and 50 minutes. So you have all this time to try out stuff and click through yourself, but keep in mind that this specific instance will not be open after. Okay. But I think then hopefully everyone has the slides as well as the page or the link for the web app itself. And then I think we can start. So to start, you simply click here on Start, and then you get this pop-up of the Getting Started page. So before you begin your active learning loop, the most important question is, of course, what kind of target property are you studying? Okay, so in our case, it's the bike modulus. In some other cases, can be something else. So for example, in one example that Lukas Fopper showed yesterday in his talk, it was for acid stable oxides, it was the Pourbaix free energy. So whatever quantity you can actually define via a DFT calculation, so a calculation with FHI aims in this case, is something you can in principle define as a target property. Note that in this demonstrate tab, we only have the bike modulus here enabled. We have also other demonstrator apps that we have already written, but keep in mind this current one is only the bike modulus. Okay, and then what we will work with is the demo project. So if you click here in the upper line on the demo project, you can get the pop-up to load this project, which we'll just do now. And loading gets you here to the next page. I'll just click to some of the slides. Yeah, and then here's a note also, because now we've loaded this example, please save this project name somewhere in a node or whatever on your local machine. So this is a unique identifier for your machine and or not for the machine itself, for the project that you're currently running. So please save this. This can be used to reload your project in case you close down your browser window, reload or whatever, and it refreshes the page. So you can simply use this project name to recover your current state. And okay, so what we've done already is we've loaded the test project where we look at the bike modulus, a quantity that we want to maximize. Now, what is loaded also when you load the template are some quantities here. And in our case, it's the calculated materials as well as the candidate materials spaces. In addition, what you need is also a structural template file. So that means because we want to run FHI aims calculations for the different candidates, we need to know what kind of structure these different candidates have. So that can be, in our case, just one geometry file here in the structure AB03 for the perovskites, single perovskites in our case. And geometry.in is the geometry file for FHI aims calculations. Okay, so that's why in our case, this is enough. If you have a more sophisticated workflow where all your candidates have different geometries, that's also possible to be done. You can load all these in here via an ASE database file. Okay, and some more details are also written here in the info box. So if you click on the right-hand side of download example, you will get some more infos here, as well as if you scroll down a bit, you will see some more infos here on what is actually accepted. Okay, but in our case, these have been loaded in advance. So you can simply click here on the next button. Now, before we actually go into the, or let's say like this, we have just loaded the training set, so our initial data set of the different materials we have and the calculated bike modulus quantity. So, and we know the primary target property in our case. Now, the next step is to select primary features. So if you have listened to a talk yesterday by Tom Purcell, who introduced a bit SISSO and SISSO++ and what this AI modeling actually needs, it starts at primary features. So we first have to define somehow physical quantities for all of your candidates and training data, which you think are relevant for your target property. And then in the app, we have two different kinds of these primary features that one can select. So that's user-provided features. This just means these features were in the initial spreadsheet. So when we loaded, in our case, the test project, For each row of a material, we also have different provided features. And these are just loaded here for you to simply, with the checkbox, load and unload. So these can be here, for example, atomic radii of the A and B elements. Here, all kinds of cation radii as well. These can be here the atomic numbers of your elements in the material, as well as, for example, here the atomic stiffness. And on the other hand, so you have the user-provided features, we also have some predefined atomic features. And these are loaded by the atomic features package. So if you click also here on the info button, you will also find a link to this atomic features package. And these are really optimized for SISSO analysis and can be imported also in your own work. So this gives you access to pre-computed per element properties, such as atomic radii, electronegativity, and other properties, which can be loaded in advance and then simply selected here when you try and select primary features. So you can essentially augment your user-provided feature space with also these predefined atomic features. Of course, you are free to play around, so you can add more features or remove them and see how the modeling that we'll look at in a second changes. These have been pre-selected in our case. We found that this selection gives you a good balance between a good enough model versus cheap computational cost. But of course, you can select more. The only limitation we currently have in this demonstrate app here that we're using is that we cannot select more than 20 features. The only reason we're doing this is to limit the amount of model training time for all the participants. So we'll just stay with the default selection. Then you can click here to continue. This will now add in the futurizing step all your primary features. And keep in mind, once you have selected your primary features and then we train the first model here and go into the active learning loop, you cannot go back. So if you want to play around first with different features and so on, please do so in these two steps before you actually go into the active learning step, which we'll see in a second. Okay, but before I continue, yes? Great, yeah, that's a great question. Thank you, SEM team. Is there any other disadvantage other than compute time to just choosing more parameters? SISSO should be able to deal with highly correlated features, right? Yes, you can use, of course, correlated features. That's also the idea of this compressed sensing, right? So you actually, in the end, you will only use a few of them in your descriptor quantities. One big disadvantage is, of course, compute time. And as you've seen, if you've seen the talk from Tom Purcell yesterday, there is this combinatorial explosion. So at some point, you're not just limited by the time to train the model, but actually just constructing the feature space. So at some point, you have just too many features. So this is also the limitation. We would say here, really, you can plug in as much as you can for the primary features as long as you think they're relevant. Yeah, it's worse basically to have a model where you don't have enough primary features that are relevant to your problem versus the one where you have more. And then at some point you will see where the actual limitations are of your machine and where the system modeling breaks down. And then maybe you have to throw some features out. But to answer the second part of the question again, yes, it also deals with correlated features. So that's no problem. I hope I answered the question, but of course, feel free to ask a follow-up if this has not been satisfactory for you or you have any other additional question. But thank you for the question. Any other questions here in this futurizing step or any of the steps before we actually continue? Okay, I don't see any, but again, please feel free to ask a question whenever. We're happy to answer. So the next step then is once you have the primary features, you go to the actual SISSO model. And these are really now selecting the hyperparameters of your SISSO model that will also be used throughout your active learning loop. So what we are not doing is updating the model parameters during the different active learning iterations. We're rather setting them once in the beginning, going into the active learning loop, and then using these parameters to construct all the models. So just keep this in mind. So once we do the model training here and we go to the next step, you can't really go back. As an alternative, if you have done so and you want to try some other stuff in the active learning, you can simply open another browser tab, navigate to the same website for the web app, and just start a new project. And that is also completely fine. You can start multiple projects here on our platform, in this case, in this instance, so that's no problem at all. So please feel free to play around also. So we went for the futurizing step. We're now at the SISSO parameters. In our case, we have some limitations, again, to reduce the time it needs to train the model. In our case, we're restricting the SISSO model to a two-dimensional model. That means you will gain two descriptors for your problem, which are combined in a linear model. And these are really the features that we'll use in the end for the SISSO model. And again, SISSO, in our case, in the backend, SISSO++ is the software that is used to create the SISSO model and all the reports and so on. And if you're really interested in these hyperparameters, so that is not necessary specifically for this example here, but you can take a look at the different parameters that have been set here for SISSO. So in our case, for example, here, the descriptor dimension, again, this is dimension 2, as I mentioned, meaning you will get a two-dimensional model. The subspace size, the maximum rung, so that is the height of your binary expression tree, and the number of residuals. So if you have listened to Tom Pressett's talk yesterday, these at least should sound familiar to you. Again, these are hyperparameters. More details are also mentioned here on the reference page of SISSO++. So if that's something you're really interested in, please feel free and play around or take a look at the reference page also. And again, I want to point out for this specific demonstrator app, we are not interested in finding the best performing initial model, which might be very complex, right? So maybe for this specific problem, you maybe need 4 dimensions, right? That gives you a lot more complexity in the model, but the gain in performance is not necessarily what we need to get a good active learning loop going. So we'll stick with these default parameters for now and click here to start our first model. This will run the SISSO model in the background and give you here a short report based on the training set. So keep in mind, these are the 200 materials that we have in the training data. We train a SISSO model with these hyperparameters, and you gain something like this. So you have your linear model with 2 descriptors. Again, as I mentioned, a two-dimensional model. Here you have a descriptor 1, which includes here the radii of the atoms as well as the atomic stiffness. So in case you don't know, atomic stiffness is a quantity that was proposed some years ago in literature, which describes more or less the elastic moduli of a material per element. Okay, so this is, let's say, it's highly likely that this should be correlated with the bulk moduli of an actual material, which is why we would expect this to be inside the descriptor space, and indeed, in this case, it is, as well as you can see here, for example, the atomic number of the B element. Now, you might say the fit, okay, it doesn't look perfect. Of course, here, as I mentioned, the R2, the R squared is not something like 0.7. As I'll show you in a second, we don't necessarily need, again, the perfect model here. But even then, the RMSE of 0.12 is, in our case, good enough for what we want to achieve with the active learning loop. Okay, and on the right-hand side, you can see the materials property map. So that always shows you the target property in terms of the 2 descriptors. And you can see here, this already allows us to somehow order the different training data in terms of target property quite nicely. Okay. So this is the initial model. And as I mentioned, once you click on next, you will not be able to go back and change the settings. So if you still want to try out stuff, for example, change the SISSO parameters, go back and change the features, that is still possible. Once you click on the next step, you will be in the active learning loop where then you cannot change these anymore. Are there any questions before I actually go to the active learning loop here? I just leave you a minute or two if you just want to play around in this case, or you're still doing some other stuff here before we go to the next point. Okay. So at the moment, I don't see an open question or a hand. So I think we can continue. Again, if you run into any issue or trouble or have a question in general, just ask whenever. Happy to help. So let's go to the next step. And this is really the active learning loop. So we have basically everything we need. We have a target property we want, in our case, to maximize. We have the data sets. So that's a training set in the candidate space. We have the primary features that we feed into our model, so the SISSO modeling, and we have the actual initial system model based on some chosen hyperparameters. So again, keep in mind, the chosen hyperparameters are not optimized to give you the best model, but they give us a good enough model to showcase here what the active learning approach does. Okay, so then the next step is how to use all this to then you do active learning. And again, in our case, we do this is basically Bayesian optimization. So what you need is an acquisition strategy. And they are, in our case, in this demonstrator, 4 different ones. You can also click here a bit. There's also this nice blog entry where you can read a bit and the references within that blog entry to see what these different acquisition functions do. But there is the random acquisition. So that just means you randomly select candidates from your candidate space without ranking them beforehand. And otherwise, we have 3 different options. We have the probability of improvement, expected improvement, and upper confidence bound. And all of these somehow take into account the uncertainty of the, in our case, SISSO modeling. And the way we do it in the backend, so how do you get uncertainty in this AI model? We do bootstrapping. So that means you take 10 runs of the SISSO modeling with slightly differing training sets. So you don't take the full training set that we have in the beginning, but rather you kick out some elements and you do this randomly for a total of 10 times. That means your model will give you random results or slightly different results in each of the 10 runs. That also means for all the candidates, you will get slightly differing target properties. And this allows you to define then a type of uncertainty because you get essentially a mean value and a standard deviation for all of these different acquisition strategies, for all the different models. And with this, you can apply different acquisition strategies to rank them and choose the best, what you think is the best one. So that means sometimes, you want to explore a bit outside your current training space, or you want to focus more on your local maxima that you already have in your training set. And to define also this ratio between how much do you want to exploit your current training data versus how much do you want to explore outside of your training data. There's this exploration parameter. So in principle, it's hard to say what kind of value you should choose here. Please feel free to play around. You can choose different values. But the guideline is the lower you choose the exploration parameters for these 3 acquisition strategies, the more you tend to be towards exploitation, meaning you are sampling more around the local maxima of your current data set, versus if you want to do exploitation, so you really want to search outside of the current local maxima that you have, you can increase this parameter, of course, as well. This will depend a lot on what kind of data set that you're looking at in your own work, what kind of parameters you choose here. We chose some reasonable defaults for what we are looking at here in this specific example. But again, feel free to play around, use different values here to see what your loop will actually give you in the end. And then in the end, what we also select is the calculation method. So in our case, I mentioned already to you in the beginning, our data is pre-computed. So both the training data and the candidate data has been calculated in advance with FHA aims. So there's no need to actually run the workflow once again here. And we disable it in this case to save some time. So all of the participants can run the tutorial quite easily several times within the time frame. So in our case, we just copy the results from the candidate space, which have already been calculated before. So let's say in our case, we want to run the random acquisition for one step. We just click here on the next material, and here we will see some statistics throughout these different steps. So let's say I just run this acquisition here. Random is relatively quick, right? You just pick a material from your candidate space, you copy over that bike modulus into your new calculated material space. And what we see here on the left is the histogram of all the bike moduli in your new data set. And in red, you will see always the iterations of the active learning approach. So in our case, we found a new material which has a bike modulus of around 0.98. And on the right-hand side, we see what we have defined beforehand as the active learning success rate. So what we define as the goal of the active learning approach, of course, to maximize, but in our case, the specific goal is to find anything above 1.35 target bike modulus. And that's what we define as a success. That is based more or less on the training data. So as you saw in the beginning, on the histogram of all the training data as well as candidate space, we stopped at roughly 1.3 EV per angstrom cubed. So that's more or less the goal that we want to, of course, go beyond in our case. Down here, you will also see the two spreadsheets. So that's the calculated materials and the candidate materials. All these columns are sortable. So for example, you have the bike modulus here, so you can always see what is your current maximum. So as I said, roughly 1.3. You can sort by active learning iteration. So for example, here 0 is the first iteration, and it has been acquired with a random acquisition strategy. And then you see here also all the features that were already in the spreadsheet. So let's say, okay, we'll do random for, let's say, 4 more iterations just to see what happens. Do we find good materials? For example, here, we actually found a good one already, something like 1.38. And then we just keep running this for these 4 iterations. And what have we seen? Well, in 5 iterations, we found 2 hits. Yeah, you can see that's why this line here is going up, stays flat, and then goes up again. So what have we found? We sort by active learning iteration. So we found here a material at 1.36 EV per angstrom cubed and one with 1.38. But again, if you sort here in the candidate space, these are still not nearly the materials that we are really interested in. So these are not the materials with the actual highest bike modulus in the data set. So of course you can run this now however long you want, but we're really interested in trying to see what is the advantage of active learning. So let's do as an example, we'll choose here expected improvement. I don't want to, let's say, suggest any of these strategies. So different ones might be better in different cases. So it's not a case of saying this strategy is better as this one. The idea here is to show any of the strategies, if you have chosen the parameters correctly, should be better than random. So that's really the idea here. So let's do, for example, 3 iterations with the expected improvement and an exploration parameter here of 0.01. So that still skews more towards exploitation. So we'll do this in the app, and this should be hopefully relatively quick. You always see here also a quick update on what material you're currently working on. Remember, in the acquisition functions, this will take longer than the random because you have to bootstrap and train 10 different models for each iteration. So you train 10 SISSO models here to get the uncertainty of your prediction, and then you choose your material. So for example, here, 1 iteration was, or 2 iterations are already done. So you can see a nice hit. So this is already higher than what we had in the random sampling, 1.43. We have now one with 1.34. So that's slightly below the target. We have another one now at 1.45. And you can see here, you can simply populate your upper region And of course, you don't have to stick with expected improvement. You can also do, let's say, we do through 3 iterations with upper confidence bound. So you can mix and match, of course. And then we see how many iterations do we actually need to do if you want to find more or less the best performing materials here. So we have 1 iteration with UCB here. We get a material at 1.46 EV per angstrom squared. So again, a nice hit. You can already see here, this is already a lot steeper. So you get an average more hits than you would with just random sampling. Again, another hit here with upper confidence bound. Again, another hit, and so on and so forth. So you can play this game and you try it out yourself, change the exploration parameter to very large values, for example. That would mean you also sample different values, maybe for lower bug moduli, just because you are biasing a bit more towards the uncertainty here. And that's still, of course, completely fine. What I wanted to show you as a brief comparison here, before I show you the actual end result. So you have, again, here all the updated material. Your SISSO model is also updating throughout. So in each active learning iteration, you gain more training data. So the model should perform a bit better, and indeed it does here. So we got something like 0.7 R squared to 0.73. And of course, this will get better the more time goes on. But keep in mind, the hyperparameters are set to what they've been set before. Okay, so this will not change here. But again, you can play around with this as much as you like. I want to point out before I show some of the results we have obtained with this before, I want to show you here briefly the download section. So what you can do is you can download all of the things that have been calculated in this active learning loop. So that means the aims output. So that's the raw output from the FHA aims calculations. If there were any, in our case, there were none because we only copied all the files over. You can download all the SISSO models. So that is essentially the SISSO++ output for every active learning iteration. Keep in mind, we have the bootstrapping in each active learning step. And you can download all the data files. So data files in this case here are the spreadsheets for the new calculated materials as well as the candidate materials that are left. So essentially, these tables here, which you can then use, of course, after for more analysis or however you like. And then again, please feel free to play around this, download the results if you like, and so on. And what I show you here briefly is what we've been able to obtain. So these are results from the app with just the default settings. So here we don't change anything. So we just click through the app, go to the active learning. What we do then is we take each of these acquisition strategies, so the 4 different ones we have, we run the active learning loop 5 times for each to get some statistics. Now, you might ask, okay, what is the actual difference between just running this active learning loop for 5 times? The difference is in the bootstrapping part, because you always train on randomly selected parts of the test data. So this will always give you uncertainty, so some random uncertainty within the bootstrap. That's why you get different runs here. And what you see always in the colored lines, this is the average of over all these 5 runs. And the shaded lines here is the uncertainty. So, and that's basically what you see here. So on the left-hand side, you see always the maximum observed bug modulus. So that's as a function of active learning iterations. In total, we ran this for 50 steps each. And one thing you can see right away is that the random sampling here shows that you can find better materials. And yes, that's possible, but it takes quite a long time to actually find good materials. And you can see that at some point, in our case, you were, for example, stuck in this range of up to 50 iterations. If you go from some roughly 15 iterations, in our case, we were not able to find anymore the really best performing material. And the best performing material is here shown by this dashed line. So you can see it overlapping with some of the other lines, but this is this dashed line here. This was this material roughly 1.48 EV per angstrom cubed. And as I mentioned, without even saying which is the best performing active learning strategy, all UCB, PI, and EI perform significantly better than random sampling in all of the runs. And you can actually see that in all cases, we find the best performing material in below 10 steps. So even with the uncertainty, sometimes some method is better than the other. So that's why, I mean, you can't really say which is better. In our case, on average, expected improvement, this purple line here, was a bit better than the other ones, but I would not draw any conclusions from this kind of study to say one or the other strategies is better. What we want to show is all of them are better performing than random sampling for our example here. And what you've maybe, I mean, what is also interesting is that we've shown the model itself is not super accurate, right? We have not trained the best optimized SISSO model, meaning we have not optimized the hyperparameters as much as you can, and still you gain significantly better performance in the active learning loops. Okay, you find exceptional candidates even if the model is not great. Of course, it has to be good enough. So what the threshold is, hard to tell in an actual, let's say, working example. But on average, you don't have to always perfectly optimize the hyperparameters. You just have to use a good enough model, and this gives you good candidates because we anyway recalculate the target property for all of the candidates. And then on the right-hand side, for the same runs, you see the histogram and how it develops. And you can nicely see that with all the active learning strategies, you sampled a lot of the exceptional candidates that we are interested in. Significantly more times than what you do at random sampling, where of course you also more randomly sample ones with lower bug modulus. Right? So here we consistently sample more in the upper reach. Okay. And that's basically what I wanted to show before you can play around with the app some more on your own. And there's one summary slide here. So we have now developed this user-friendly web application. It's currently in beta, as you've seen on all the pages and also in the presentation. But the idea is to allow for using SISSO, active learning, and FHI aims in a closed format to really somehow speed up this process. So even if you're non-expert, you should be able to run the combination of these within this app. It can be deployed, and we have tested it already on both local and cloud resources. And here, all the workflow management is done via Automate2. So that's a Python workflow manager, which allows us to define several target properties already. So the only limitation is the target property. For the target property, we have to write some kind of workflow. So what this workflow is still flexible, but we need to be able to implement some kind of Automate2 workflow to obtain that target property. So that's, of course, a limitation. But in general, if you're interested in trying this out on your own or maybe in some of your own work, please contact us. So if you have some workflow you're really interested in, where you think this kind of modeling could be useful, feel free to look at our webpage and the contact information there, or write directly at aimscoordinators@ms1p.org with some more information. So maybe you let us know what you're interested in, and we can try and work on this as well with you together.